Welcome NPTEL course on principles and techniques of modern radar systems. In the last class, we have seen the delay resolution constant. Today, we will see the Doppler resolution constant. Now, for rectangular pulse, the delay resolution constant came out to be 2/3 T. Let us call that. It will require a number. I think it is previous was 53. So, this should be 54. This should be named as 54. So, now we come to the Doppler resolution concept. So, again the similar concept, we know that the ideally again I can say the except FD that should be peaky or impulse about FD is equal to 0, and in all other places it should go to 0, but it does not happen. So, again in general it will have this shape, some arbitrary shape, and again to put that equivalence we will put a rectangular function here with the peak, and the energy of the two will be constant. Energy is a fundamental parameter. So, energy of these two graphs or area under these two graphs are same, and this difference is called the Doppler resolution constant. So, this peak we know, this peak is 0 and this function is this. So, again this is except FD, sorry, this is square. So, this is except 0 square. So, we can say that the minus infinity to infinity So, this again can be, so first let me give it a number. I think earlier I have given 54. So, this is 55, and in terms of, because ambiguity function may not be always known to other people. So, we should write it in terms of autocorrelation, that minus infinity to infinity r x6, and remember that in case of Doppler it is minus FD that we have derived earlier. So, this we can call equation 56. So, now the question is, again, instead of doing this, if we can do it in the time domain, that is an alternative one. If you know these expressions from this range ambiguity Doppler ambiguity function, then it is okay. Otherwise, again we will do some mathematical manipulation to have an alternate expression in terms of signal energy and also time domain things. So, for that I am doing some mathematical thing, that we know what is the inverse Fourier transform of this XFFD. XFFD is nothing but this function. If we do not write it as a two-dimensional function, I generally write it like this. So, what is this? This is minus infinity to infinity XFFD e to the power j 2 pi FDT dFD. Please remember, here running variable is Doppler. So, that is why this is FD and running variable is FD. So, again we have earlier defined this function. So, we can put that definition. So, in terms of the spectrum, so again I can take, because FD is the running variable. So, XF I can take out. Now, we will have to put a change of variable. So, df has come here. Now, change of variable, put this f minus f d is equal to, let us say, z. So, if you do that, you will get something like this. In the second integral, put here, do not put it here unnecessarily. So, we will get that minus infinity to infinity this, please correct it, this is simple one, x z e to the power j 2 pi f minus z t, then minus dz df. This is as it is, and from here also this f term can be taken out, j 2 pi f t, and so we are left with here this x z e to the power minus j 2 pi f 2 pi f 2 pi z t dz then df. Then again you can have a substitution here, because it is a frequency domain term. So, you can one more substitution is required, put minus z is equal to u, and so you will get the again in this one only. Do not do it here unnecessarily, that won't help anything. So, here it will be x minus u e to the power plus z. So, it is, we can write it as this whole part we can write as x of t. Please see, this is the basic definition, and then there will be df. It is simple because spectrum is symmetric. So, x minus z you can again put x plus z, because all for real signals all spectrum is symmetric. So, I should write here that symmetric spectrum for real signal, and other signal is always a real signal. Okay. So, this x t I can take out, and what is this? This is what is left is the inverse transform of. So, this is nothing but as simple as that. So, now we have got an important relation, and this will now put to. So, I think we should give the numbers where at the last 56. So, I can give it a number. This is 57. What is it? This is the IFT of except FT. That is this. So, we can say that Fourier transform of this x t square will be this. So, now coming back to our a thing, that what is minus infinity to infinity because this is in our Doppler resolution constant numerator. So, that we can say that this is in time domain it is nothing but and also now this also can be written in terms of cross correlation as autocorrelation, that R x x minus f d whole square df. So we can easily write that the Doppler resolution constant is nothing but minus infinity to infinity by we know R x x 0, this is E x, so it is simply the E x square. So you see in both the resolution constant we have the E x square, only in one case it is x f whole to the power 4, in this case it is x t whole to the power 4. So actually this I can give it a number. What is this number? 57. So this will be 58, equation number 58. So we can do it for a single rectangular pulse. So for a single rectangular pulse, we can find this, that what will be this x t, we know the value of x t, it is a rectangular function. So this, so I can say this will be a to the power 4 t, and the energy of the signal is a t s square t whole square. So this will be 1 by t. So we can give it a name. This is 59. So, single rectangular pulse, the Doppler resolution constant is 1 by T, and the delay resolution constant we have seen it to be 2/3 T. So, now what is the product of these two? So, it is instructive now to make this product that this product comes out to be 2/3 T into 1 by T. So, it is 2/3, that means 0.667. Okay. So, you see that the effect of all this is resolution in delay and resolution in Doppler, their product is constant. So, if you want to have a fine resolution in one domain, the other will always be suffering. So, this is a drawback, that means, because if you want to make one smaller, the other will increase. So, that is a very bad thing, because we want measurement and we want both of these measurement to be precise. Actually, we have seen earlier also that in ambiguity function, if we have the card that in range it is giving very good resolution, but we are getting a very poor Doppler resolution. So, if we use a single rectangular pulse, this is the case. In next classes, we will see more realistic cases that a number of a pulse train, but still we will see that we cannot overcome this. Then we will finally see a technique called linear frequency modulation or CHARP, where we can overcome this, because these things should not be a constant. If this thing be a constant, then we are at a trouble, but if we have this at a designer's hand, then we can have both these resolutions improved to whatever extent the physical hardware permits. So, that we will see in the next class. So, today what we have seen? We have seen the two important concepts in resolution. One is the delay resolution constant and another is the Doppler resolution constant. This is Doppler resolution constant. So, if we know the expression for any transmitted waveform, we can find these two things, and these actually determines the resolution of the radar detection. Thank you.